Okay, everybody, let us get started here. Just want to connect to the schedule that you can expect over the next week or so. Today is the 29th, of course, and according to that, we have this day and the next, 2 more full days worth of new material. It may all fit into today. It's certainly not going to take 2 days. If works out the way I hope, we'll start reviewing on Wednesday and also review all day on Friday. As part of that, we're going to end up doing quiz 3. Right? I don't know if we'll do it on the quiz form itself. The review document I bring is just the quizzes expanded to allow extra space for writing stuff down and so forth. So we will do at least most of quiz 3 in class starting tomorrow and no later than Friday. And the reason I do it that way is you're coming up on the exam on Monday, a week from today. You need to have 3 graded quizzes to study from. Okay, the exams are very much built off the quizzes, partly due to laziness on my part, but also because why do we have quizzes if they're not going to be useful for the exam? There's supposed to be a little run at the exam in advance. So expect that. Still do when it says here, but you'll have the answers in one form or another kind of built up as part of the review. All right, that's where we're headed. Not 2 more days worth of new material, maybe only 1, but we'll finish all that pretty comfortably here pretty soon. All right, with that in mind, as a launching point, here's kind of where we left off. That would have been on Friday. We're talking about different ways to regulate an enzyme, and this is kind of starting out in the middle of nowhere with method 3. Here's a very, very miniature review. You don't need to write this if you don't need to, but let's just review what the first 2 methods were. Does anybody remember the first way to regulate an enzyme? Big picture, we took maybe an entire class or a little bit more on it. I hope the word inhibitor comes to mind. And the second method was, there's this route called allosteric regulation. So sometimes an allosteric regulator will make the enzyme go faster, sometimes it'll make it go slower. Inhibitors can be either competitive or non-competitive. Okay, so that's optional and extra right there. That's just a way to kind of make sure that you know once you see a number 3 that, oh yeah, there's a number 1 and a number 2 as well. We've been through them, and if you're kind of on top of those, this little extra note is just extra. So like it says here, here's number 3, and the tone it sets here should kind of make everybody sit up and go, oh really? Because if you're talking about changing the primary structure of an enzyme, this is drastic. This is the most brutal way there is of regulating an enzyme. Now remember what a primary structure is. If you remember this, you don't need to write it. It's a list of amino acids in order. And the order is, of course, nitrogen to carbon. That in itself is a little review. What this is saying is you're actually going to monkey with the basic structure of the protein. By the time you get done with this regulation, what you start with will not be the same molecule. And sure enough, here's the principle of how it works. You start out with a large polypeptide, a protein. Sorry, I'm making that focus flicker a little bit there. This is a precursor, and it has a name which you may have heard before. This thing is called a zymogen. It is an honest-to-goodness protein, and this thing is not as active a catalyst as your smaller polypeptide. All right, you start off with that. It's made at a select location in your body, knowing that it is not as good a catalyst as it should be. So you got to start somewhere, and this time you start off with a protein, and then in the middle of it, there's going to be another enzyme to catalyze this. It'll be fair to say this. Another enzyme catalyzes this. And then here's the regulated version. This one is very active. This one is made by, of course, and I'm putting a story on the words in the title, a reaction. It's made by cleaving the zymogen. Okay, start out big, go to little, thanks to, in the middle, yet another protein involved. And this is a way of making an enzyme. Again, this one's active, and the other one is relatively inactive. It may not be totally inactive. And you might think, well, why on earth would something this complicated be necessary to make an enzyme? And here's why. Do know these. These are critical to digestion, metabolism. The main example is the peptidases. So look at what they're doing. These are proteins whose job in life is to break down other proteins. Now, if you've had A&P, which many of you have, you will have at least heard about this before. We think about it as a kind of a molecular phenomenon now. And there's a family of them, family of zymogens, that look like this. It turns out that your stomach actually makes its own digestive enzymes. So, why is it that the stomach doesn't destroy itself? Right? That'd be a fair question. The stomach muscles are, they have protein all over the stomach structure itself, but yet here it is making its own digestive enzymes without destroying itself. Well, reason number one, the acid in your stomach doesn't destroy it because you've got mucus all over the inside, so that creates a big barrier between the contents of the stomach and the walls. But look out, because if the stomach were to secrete the active enzyme into its own lining, it would destroy itself. But what happens is you make the enzyme called pepsinogen. It's secreted from the epithelia of the stomach out into the inside of the stomach, and once it's there, it hits a pH and another enzyme that breaks it down to this one. Again, this one's active, this one's inactive. It's a way of separating where something is made from where you actually want to put it into motion. You don't necessarily want peptidases, things that destroy proteins, to be active just anywhere. And here's another couple of spectacular examples, trypsinogen and chymotrypsinogen. They're actually made in the pancreas, and then of course, it has a duct that dumps into the intestine. You certainly don't want active peptidases running around in the pancreas. Okay? Pancreas would digest itself in a matter of a short time. So that's why you need these. You need to know these. Know these large precursors that don't do much to help digestion. And also, here's the real action taking place thanks to these smaller ones. These are your smaller active enzymes that do what they are headlined to do. Get this, they destroy proteins. So there is indeed a whole, I want to say, marketplace of proteins inside the cell, outside the cells, some of them roving around looking for other proteins to destroy, the whole thing choreographed really well and in balanced. Some of them being made, some of them being destroyed. Don't ask me how it all fits together as well as it does, but it does. All right, there's a method of regulating an enzyme. That's the only one. That's the last one we've had. That's your list up to a total of 3 now. Inhibitors, allosteric regulation, and changing zymogens into active proteins. That's your list of 3. Okay, so we'll look at only one mechanism. And if you just came out of organic, you're going, I thought I was done with that. I think your chapter summary has a version of this that's a little on the scrimped side. You probably have trouble filling it all in with enough space. So I've got a few extra copies here with more space. This ended up printing it on 2 pages. So speaking of the proteins that are active only in the right place at the right time, here's one of them. Chymotrypsinogens, made in the pancreas, active in intestine. There it is. Made in pancreas, active in the intestine. All right, chymotrypsin is one of a family of enzymes that are called serine proteases. The serine part you don't need to worry about too much, but here's a heads up. The fact that it is called a protease means that its job is to destroy other proteins. That's what the term itself means. All right, as with any reaction mechanism, you need to start with the reaction itself. Callista, you're squinting. This says breaks protein. All right, made that a little too small. All right, so here is an abbreviation for an entire protein, and we're going to focus on only one bond that matters right here. So let's say that this piece right here is a protein. Here's the nitrogen terminus, here's the carbon terminus, and we're working on just the one bond which we called earlier an amide bond. That one right there, if you're looking over to your product side, that one there is going to break. So again, when it's all done, you're looking at a smaller protein. R1 and R2 are both abbreviations for, it could be this whole long thing. We're looking at how you break only one bond. And what we're talking about is an amide plus water going to, as far as that one bond is concerned, a carboxylic acid and an amine. Okay, if you took organic recently, you have seen this reaction before. Now, you saw it on little versions of the same thing. This is your organic reaction scaled up to happen on the size of an entire protein. Okay, there's a term for this, and it is hydrolysis, because you end up breaking water with part of the water winding up in one piece and the rest of it ending up in the other piece. All right, so let's talk about the mechanism. I hope you remember a little bit about organic to know that the most vulnerable spot in this unit right here in an amide is, first of all, that carbonyl carbon. Partial positive, so anything with a lone pair of electrons is a likely partner. The other option would be the lone pairs of electrons out here. They could find a Lewis acid. Okay, let's just kind of make sure we're in familiar territory. So the mechanism. We're talking about step 1 right here. It says that serine, which is a nucleophile, attacks the substrate carbonyl carbon, And so the mechanism is something that we call a serine protease. It has actually 3, but I'm going to show only 2 important spots. The ones shown here are serine and histidine. This set of 2 is always going to be important. Somewhere between the 2 of them there's other stuff in the protein. That's why this is in here. But don't worry about that. They're strung together and they're held together in 3-dimensional space thanks to the stuff that we've already had about protein structure. There's secondary structure. There's localized winding. There may be some folding that takes place. Whatever it is, nature has designed not just these 2 spots, but the whole protein, so the whole thing holds together these 2 things in just the right way. Okay, pretty cool. That's a mark of a good catalyst. We're miles in effectiveness above sulfuric acid, which knows how to dump a protein and then it's done, or proton, and then it's done. These are things doing the right thing, the right time, at the right place. Okay, no wonder it's good. All right, so here's serine, and it has on it to begin with a hydrogen. That's what serine, its R group is just an alcohol. Looking at it like this, you'd think, oh, this is no more sophisticated than ethanol. You know, if there were a methyl group up here, this would be a little molecule, and here's an amine. And switch colors here. The nitrogen definitely, to complete its Lewis structure, has that much on it, a lone pair. All right, what we need to do is explain how this catalyst up here interacts with this set of bonds up here to break and form. So I'm going to keep this pretty close and maybe reorient that carbonyl group so that it looks like that. Is that big enough that you can see it, Callista? A mechanism is no time to make things look more obscure. Okay, that's the core right there. There's the amide bond, which has to have a carbonyl, has to have a carbon-nitrogen bond. Then there's other stuff on it. So, okay, out here we have R1, and the nitrogen would have on it a hydrogen and the rest of the protein. Okay, there's the reactant that bumps around and comes in contact with this set of 2. All right, don't forget, again, full Lewis structures on the portion of the molecule that does the reaction, and that means we better be tracking both the oxygen and the nitrogen in the protein. So there's 3 lone pairs to take care of, and now everything that's going to be involved you can explain with real Lewis structures. Okay, first thing that happens is this, and I don't know if I should say the first thing, it happens all at once. You've brought an oxygen with a lone pair close to, thanks to a collision, close to a carbonyl carbon that's very able to accept it, and you've drawn this dozens of times if you've drawn it once. You knock one of the pairs of electrons that was holding carbon and oxygen together just out onto oxygen. Okay, that's one step in making an ester. It's one step in making an acetal. It holds carbohydrates together. That's a natural pairing. Now, this oxygen, though, can't end up like that because then it would have too many bonds. Here at exactly the right spot to help by pulling off a hydrogen is this other piece of the protein, the histidine. Okay, so that means that the hydrogen is able to let go, meaning that bond right there breaks, the one between oxygen and hydrogen. And let's see what we would have to show for this. I'm going to squiggle out that line so I can draw it a little straighter down here. We would now have to have a new bond between carbon and oxygen, and the old carbon-oxygen bond is not what it used to be. There's only one of them, and you'd have a formal negative charge on that oxygen. Now that right there is probably the single most important thing to recognize. You broke one of the carbon-oxygen bonds, you're down to just one. Then, of course, don't forget everything else that was there. It has to still be riding along. That means that your nitrogen still with its hydrogen, and the rest of the protein is sitting there. And now the oxygen from the serine has 2 lone pairs on it still. And so this story now is you're going to break one of the CO bonds. Okay, the only thing that isn't shown here yet is, and I'm going to draw this in red to make it stand out as much as I can, the hydrogen transferred to the histidine. That's worth a little story. Okay, step 1. Not all that different from what you would have expected in an organic class. Okay, the next one is also not that different. You will have seen this before in your chapter on, if you remember an obnoxious chapter on esters, acid chlorides, amides, all kind of smashed together, all doing more or less the same thing. You've seen this second step before. And here's what it looks like. I'm just going to redraw what we had as the final product in that first step. So here's what matters. It's the spot where you now have a lone carbon-oxygen bond. Oh, you know what? I'm getting ahead of things, aren't I? This should be a carbon. In the blank, I tried to color in the oxygen. That should be the carbon. So what we had up here was an R1. So, yeah, stays right there. And you also had all this stuff. So that stays there. The nitrogen with its hydrogen and its R2 and its lone pair. I'm sorry, this is getting kind of squished. And here's still a hydrogen, the new one, sitting on the nitrogen. Okay, now I'm going to go back and add one more detail to both spots so we can do them at the same time. This one I hope you recognize as a spot where there's a formal positive, and so is that. All right. Here's some movements that can take place now that you've busted up that one carbon-oxygen bond. If you remember what this looked like in an organic class, I hope you remember that it was always something like this. It's like the oxygen decides, well, no, I'm not going to put up with that forever. You've got to take back part of this carbon. We were double partners to begin with. That's the way things need to go. And so, the old rule was, if you did this in organic, when the oxygen lone pair kicks back, something else has to go. Calista.
Between the CH2 and the C?
Yeah, you're right. Let's see. It's that one up there. Here's what I'm going to do. I'm going to grab a fresh sheet and draw it fresh for you. Except that wouldn't help you do a correction. Okay, let's improvise here. This needs to be oxygen, which would be that one right there. Sorry to squish this. Lone pair and carbon. Yes, thank you. So that's what I drew to begin with. That was right. Should trust that. Okay, what happens here is an electron pair reverts. In other words, it says, I'm coming back. You've seen that before in your organic class. Okay, now when that happens, something needs to turn loose, and what's going to turn loose is this bond that you can tell by looking at the reaction up here. It has to die. The carbon-nitrogen bond is going to break at some point, And as in your organic class, it would break here. Okay, so that's fine. Usually you would draw this in your organic class by going, okay, carbon-nitrogen bond, you go here. That entire pair of electrons should go to the nitrogen, except that here is a catalyst to make the whole thing even easier. The enzyme is holding a hydrogen to serve as the new partner for this nitrogen at just the right spot. That's why this is such an awesome catalyst. So it's a real easy matter to go, yeah, I can let go of that bond to carbon because I've got such a handy hydrogen nearby, and histidine doesn't care if the hydrogen goes away. It wasn't there to begin with. Very smooth move because several things are in the right spot at the right time. Now, if that's what you're looking at, here's where you are, and I'm going to believe my oxygen this time. Thank you, Calista. Okay, so we're back then to having this. We've got a bond to carbon, and we've got a bond to oxygen. There's the carbonyl, and we've got a bond to the rest of the protein. So there's R1. Okay, now notice your histidine. Histidine is now free. And let's not forget the main thing that got accomplished on the substrate, the protein. Plus, I'm going to make this its own product right here. This is your headline. Here's what else you make. You make the amine piece. It still has the rest of the protein, R2, on it. It has a hydrogen that it had to begin with. It has a hydrogen it got from the histidine, and it's got its lone pair. Okay, here's what happened. The amine is now removed. That is accomplishment number one of those first two steps. Deliver a proton, kill one carbon-oxygen bond, then restore the carbon-oxygen bond and kill the carbon-nitrogen bond. As of that point, you have officially destroyed the protein substrate by breaking it into two. Now, half of it is still hanging around at the end of step two. Half of it is still covalently bound to the enzyme. And that's what the next step is for. So step three. This is what gives the whole thing its name, water, hydrolysis. And by the way, there's a lot of this stuff around. Water will be from the outside. You can invoke water anytime you want in a biological reaction. And remember what we ended up with. In the previous step, we had this that amounted to an ester, looking like that. Okay, now water, since we know what the product is, we know that eventually this whole thing has to get knocked off of there. We also know that water is a reactant, and we know that water is a good nucleophile. So here's what it makes sense to draw. I'll have to draw some kind of long arrows here to keep these two distinguished from one another, but here's an oxygen, here's a hydrogen, and here's a hydrogen. And yes, they probably do have to slide in fairly close to each other, looking kind of crowded, the way it's drawn here. Now, you know where water is going to want to head. Its oxygen atom is a good nucleophile, so it's going to want to head straight for the carbon. Might as well draw it like that. I could have drawn it further up in there, I guess. I was trying to keep things as separated as possible. Well, same thing again. Carbon-oxygen double bond, happy to die, and send one pair of electrons out to live on the oxygen by itself. That's like a repetition of the first step. And once again, histidine is in a good place with its lone pair to grab a hydrogen, this time from water. And so here's what you end up with after that step happens. Here's carbon. Its new partners are now, or its total partners are now its original R group. its original oxygen, which now has a negative charge and only a single bond to it. And look what else. You've broken water. This is starting to look kind of hairy. That's okay. And as before, hydrogen, which creates a partial and a full positive charge on histidine. Right thing at the right place. So the story here is that histidine again takes an H plus from the nucleophile at the right time, and of course it's in the right place. The enzyme is holding it in the right place. So there's your intermediate. Two charges, one on oxygen, one on nitrogen. Okay, so let's finish this up. As of this point right here, you have a bond to carbon. I'm going to bend that a little bit. There's carbon, and it has its original passengers on it. And watch out for your oxygen. It's going to do exactly the same thing as before. Okay, I'm changing the color as I draw that OH. And here's the proton that's going to be at the right place at the right time. There's what we drew in the previous step. Okay, I think you can probably see what's happening here, because once again, you've drawn this a million times. You knocked electrons out onto that oxygen, and they don't take it forever. So it's like, I'm coming back, something else has to leave. And when that happens, what has to leave is the entire piece, and that looks like this. This oxygen says, oh, I had a hydrogen to begin with. I can take this one because it's so close to histidine. And the hydrogen then releases its pair of electrons to be back on nitrogen. And look where we are again. Okay, back to serine again, back to histidine again, and here's the headline this time. The piece you make here is this. You got your R1 and the piece that got knocked out, which is, guess what, carboxylic acid. This is the other piece of the protein. In real life, in the cells and the cavities of your body where this takes place, it's taking place right now. This happens so fast, these 4 steps happen so fast, you couldn't catch it by watching them. It takes a lot longer to step through them and understand them. But it's like if you're going to take a university level class in biochemistry, you need to know at least this much about how one enzyme works, because this is so central to digestion. So just to step through it again briefly. Nucleophilic attack on the carbonyl, lose one piece. Next one is nucleophilic attack again on carbonyl, except by water, and then lose the other piece. There will be some version of this on the exam. You need to start practicing for it now. Okay? And I'll be watching for correct movements of arrows. I think this is the only mechanism in the class. So it's not going to be an everyday thing. But this one really is crucial. If you had to pick out one, it needs to be this one. Okay, how about if you all stop writing, stand up for about 30 seconds, turn around. You don't want to be looking at your notes. Okay, by this point you're guaranteed to be glazed over a little bit. Take a break, just a brief break. Okay, how about if we start up again? We don't have much to do, and it should fit conveniently and comfortably, I think, the rest of the time. I don't know why I just thought of this, but who graduates? Who's planning to graduate in May? Are you, Calissa? I forget when you were in Quan, but it's been a while. Was it last year?
Last year first semester.
Okay. So that makes you a junior now or something. Nobody else graduates? Just one graduate? Okay. All right, so this is the last part that we need to finish for today and for the exam. It's this business of coenzymes. I guess you could say they're regulators of a sort, but the main thing to remember is that coenzymes, you have to have them for the enzyme to work, but they themselves are not proteins. A lot of vitamins fit into this category. I won't say all. Let's say some vitamins. The lack of a vitamin, if it's a coenzyme, the lack of a vitamin would show up as diminishing activity of an enzyme. That you start to see that whatever reaction that enzyme catalyzed, that would start failing on you. So you'd be building up some intermediate, or you wouldn't be making a desirable product, whatever it is. That would be the example. A lot of your B vitamins, you want to be careful. You don't say that they are themselves coenzymes. They get converted in your body to be coenzymes. So it's like they're coenzyme precursors. And you don't need any structures or anything right here. But that's the concept. What this means is you take these guys here, and in order to get to the others, you're going to have some reactions, which is okay. These things right here, absolutely required for some enzymes to work. You won't be far wrong if you think about enzymes as enzyme partners. But definitely not enzymes themselves, not even proteins themselves. They're usually littler molecules, fit some little groove or some binding site. So yeah, that is the last part that we're scheduled to cover before the exam. That takes us down to this point right here, which was scheduled to be on Wednesday. Okay, so it's working out with about a day extra. I will plan to come on Wednesday and Friday armed with a review outline. And we don't have to limit ourselves to that, but it's the quizzes expanded. So we can kind of expand on those. If you have questions or want clarifications, I'll kind of jump off the quiz documents and so forth. And I will come with hard copies. It should be available online as well if that's the way you prefer to take notes. And the next 2 days, since they're reviews, they'll be kind of free-for-alls. I'll be depending on your questions and try to expand on whatever you feel like you need to hear the most again. Okay, so we'll call it done for today, and I'll see you on Wednesday.